And to round off this session on Hamiltonian learning, we have you, Tong.
Thank you. So this talk is based on a joint work with Muzhou Ma of Tsinghua University, Steve Flammia from Virginia Tech, and John Preskill from Caltech. So before I begin, I want to thank the other speakers in this session for taking care of most of the introduction to this area. But for the sake of those who are coming only for this talk, I'll still do a brief recap. So the setup of Hamiltonian is as follows. Hamiltonian learning is as follows. We have an n-qubit quantum system evolving under a Hamiltonian H. And we are allowed to interact with the system, and the goal is to have a complete characterization of H classically. And you might imagine, because if you don't know anything about H, this may be an impossibly hard task, so we may require some prior knowledge of H. So let me explain what each of these points mean. So by interaction, I mean that we can prepare an initial state, apply unitary steering time evolution, and measuring some basis. So mathematically, everything is written down in this equation here. So we prepare initial state phi, let it evolve under an unknown Hamiltonian for time t1, apply some unitary u1, and keep doing it until at the end we do some measurement. And hopefully all the operations we apply are simple. For example, for initial state, we want them to be product states. For the unitaries we apply during time evolution, we want them to be, say, single qubit operations. And then for the measurement, we also want them to be simple enough so that everything is experimentally feasible. By complete characterization, I mean that we want to expand the Hamiltonian in the Pauli basis. And if we can figure out all the coefficients mu p, we will be able to have a complete classical characterization of what a Hamiltonian is. And as you can see here, we will have 4 to the n many parameters to estimate if we know nothing about the Hamiltonian a priori. So here we assume there's some prior knowledge of H, such as like only a Pauli n size subset of mu p's are non-zero. And we'll also assume that each of this mu p is bounded by 1 in absolute value. So these assumptions are satisfied from physical intuitions, such as if your system is geometrically local, naturally satisfy all these assumptions. In this talk, we may want to go beyond the geometrically local assumption. So this was also done in the previous 2 talks. So we focus on real-time evolution rather than Gibbs states. So people also say like learning Hamiltonian from Gibbs states is also called Hamiltonian learning, but this talk will only focus on real-time evolution. And the goal we want to achieve in Hamiltonian learning here is usually the Heisenberg limit, which is a kind of quantum-specific phenomena. So to assess the cost of your learning protocol, we use this measure of total evolution time. You can see here from this equation, what we have is what describes one experiment. We evolve under an unknown Hamiltonian for time t1, t2, all the way to tr. So the evolution time for this experiment is just t1 plus t2 all the way to tr, everything added together. And we add this up for all experiments. So that is called the total evolution time. And the Heisenberg limit, which is the fundamental limit, like dictated by the laws of quantum mechanics, it tells us that if we want to achieve precision epsilon for estimating even a single parameter, the total evolution time scaling is at least linear in 1 over epsilon. So the goal of designing these learning protocols, at least one of the goals is to saturate this Heisenberg limit. And we know this limit is attainable in unitary channel tomography, which means like if you have a unitary, you want to learn that precision epsilon in some appropriately chosen norm, you can do that with cost 1 over epsilon. However, because in this kind of very general problem, we know nothing else about the unitary besides the fact that it is a unitary, so you naturally pay an exponential cost. So this is kind of the thing we want to avoid in Hamiltonian learning scenario. So we want everything to be Pauli n. The first work that attained this Heisenberg limit scaling in a scalable way, scalable in system size manner, was this work from 2023 by my co-authours myself. So what we did was that we we attained this Heisenberg limit scaling for bounded degree local Hamiltonians, which is like a slight generalization of geometric local Hamiltonians. So then the question is, like, can we go beyond this assumption, right? So there are many Hamiltonians out there that are not bounded degree local Hamiltonians. Then came this breakthrough work from 2024 that was presented during the first talk in this session about structured learning. So the question they asked was, can we learn a k-body Hamiltonian without knowing which terms are present? So their result was an efficient learning algorithm that learns a k-body Hamiltonian with m poly terms with total evolution time m over epsilon infinity to achieve a L infinity norm epsilon infinity. So here, by L infinity norm, I mean the max error you have on all the coefficients. So we want this error metric to be below a threshold epsilon infinity. And you can see here the Heisenberg limit was achieved, and then there's a nice scaling with the number of terms, which is linear in n. And the strategy they adopted was a recursive procedure to partially cancel out terms using previously learned estimates. But in their protocol, because they need to cancel out terms, so that requires applying accurate multi-qubit gates in their shorter procedure. So that is not something you want to do experimentally, especially when you have an unknown Hamiltonian that you actually want to learn. But then they also have a very nice feature, which is their protocol achieves constant time resolution, which means like between any two operations you need to apply, there is a constant time interval. So you don't need to apply things with very high frequency, and that is a very desirable feature to have. So to compare with their result, our result is about like learning a k-body Hamiltonian with m poly terms, and we achieve a total evolution time of m to the 1.5 over epsilon 1 to achieve L1 error epsilon 1. So here you can see we're using a different error metric. It's the L1 norm. So previously we considered the max norm of max error on all coefficients. Here we consider all the errors added up, and we want all the errors added up to be below this threshold epsilon 1. So if we adopt this error metric for the previous work, then they would have a m squared over epsilon 1 scaling compared to our m to the 1.5 over epsilon 1. So you can see we do a little bit better than that. And our protocol only uses single qubit poly gates during time evolution. So initially we need a GHZ state, for which you definitely need multi-qubit gates. But during time evolution, we only need single qubit gates. So that is an improvement. However, we will require epsilon time resolution, which means if we want to achieve higher precision, we will need to apply operations more frequently. So that is not so desirable. So you can see there is a kind of trade-off here. So, but like depending on your experimental scenario, you might want to decide which one you want to choose. And our protocol also has the nice features. It has spam robustness, efficient classical processing, but these are also shared by previous works. So you might be wondering like why I'm changing the error metric here, right? Like previously everyone worked with L infinity norm, why L1 norm? So I would argue L1 norm is actually the natural error metric, simply because when you have L1 norm guarantee, you get a guarantee about how well you can approximate the time evolution operator using your learned Hamiltonian. And this is actually the purpose of Hamiltonian learning, which is you use your learned Hamiltonian to predict things about the original system. And when you have this kind of error bound, you can very nicely bound, say, the observable expectation values in this like kind of prediction procedure. So originally we had L infinity norm, which leads to an L1 norm estimate. So that is sufficient. But here we just directly consider an L1 norm, which is also sufficient for the purpose. So the main technique we use is compressed sensing. Here I will give a very brief introduction. So we consider an underdetermined linear system AX equal to Y. So because it's underdetermined, you cannot possibly uniquely pin down X just from this linear system. But if we're given additional information that X is M sparse, then there's some hope of doing that. And in particular, if this matrix A has the restricted isometry property, then everything becomes a lot easier. So here by restricted isometry property, I mean that for M sparse X, this matrix A essentially behaves like an isometry. It roughly preserves the norm. So with this nice property, X can be recovered through a convex optimization procedure. So we just minimize the L1 norm of X subject to the constraint that AX is not very far away from Y. And this convex optimization problem can be solved efficiently on a classical computer. And another nice thing to have is it's robust to noise. So you can always incorporate the uncertainty into this parameter alpha. So with comparative sensing, we are actually ready to deal with some of the most simple case, such as a diagonal Hamiltonian. So we consider M sparse diagonal Hamiltonian of this form. So H is a sum of Z strings, each with a coefficient that we want to learn, and there are M of them, M non-zero entries. So a key observation is that eigenvalues of this Hamiltonian can relate to the coefficients in a really nice way. So because this is a diagonal Hamiltonian, we know the eigenvectors, which are just computational basis states, and corresponding to each computational basis state, we have an eigenvalue, which is related to the coefficients via Walsh-Hardy-Marsh transform. So a direct way to get the coefficients mu b is just to estimate all the eigenvalues, invert the Walsh-Hardy-Marsh transform, and then you get all the coefficients. Right? But in order to do that, we would need to get all the eigenvalues. And there are 2 to the n many of them, which is not something we want to do. So we can ask this question, like, what if we only have a small subset of the eigenvalues? Like, if we only have gamma eigenvalues, where gamma is much smaller than 2 to the n, can we still do that? Right? But looking at this linear equation that relates the eigenvalues to the coefficients, we can see that this is an underdetermined linear system. There are much fewer equations than observable than variables. But the nice thing we have is that this coefficient matrix has restricted isometry property, which allows us to directly apply comparative sensing to recover the coefficients from eigenvalues. And eigenvalues can be very nicely estimated to the Heisenberg limited scaling using robust phase estimation proposed in this previous work. And so this is for diagonal Hamiltonian, but we don't want to stop here. So then can we do Hamiltonians that are more general, right? So the easiest thing to consider is what if we change the local, like a single qubit basis, right? So if we just change the single qubit basis to be, instead of Z1, Z2 all the way to Zn, we do it like Z1, X2, Z3, Y4, this kind of thing, then basically nothing changes. Everything is the same as up to single qubit rotation. But we want to deal with a more general Hamiltonian that may not be diagonal in any single qubit basis. Then the technique we need to use is this Hamiltonian reshaping introduced in this 2023 paper. So what Hamiltonian reshaping does is that it gives us an effective Hamiltonian that contains terms from the original Hamiltonian, but you can select which terms you want to preserve and which terms you want to throw away. In particular, here we only select terms that are diagonal with respect to a chosen single qubit basis. And this procedure only requires inserting single qubit polygates during time evolution. So once we have such an effective Hamiltonian, we can just directly apply the comparative sensing protocol I described in the previous slides to learn the coefficients mu p. But as you can see here, we can only learn some of the coefficients in one effective Hamiltonian. So what about the others, right? So this tells us we need to choose multiple effective Hamiltonians to cover all coefficients in the original Hamiltonian. And turns out we can just randomly choose the basis. And each term, because it's k-local, it involves at most k qubits, it will be covered with 3 to the minus k probability. And if we want to cover all the terms, we just do 3 to the k times log m over delta rounds, and everything will be covered with probability 1 minus delta. So this only introduces a very mild overhead. So with that, I'm ready to describe the learning protocol. So we first prepare the initial state, and then choose a single qubit basis. And with this initial state, we run time evolution by evolving under an unknown Hamiltonian and inserting Pauli operations. And the Pauli operations we insert will be decided by this single qubit basis we choose. At the end of the experiment, we do measurement, which tells us about the eigenvalues, and we then feed these eigenvalues into the L1 minimization problem coming from comprehensive sensing, and then helps us recover the coefficients we want to learn. So this is about the protocol. And we also have a lower bound result in this setting. So to learn m parameters for fixed terms to procedure epsilon 1 in L1 norm, the total evolution time is at least m over epsilon 1. So we can compare with our upper bound result, it's m to the 1.5 over epsilon 1. So you can see there is a gap of square root of m, which is not entirely satisfactory. So this is because in this lower bound, we're considering fixed terms. So the difficulty of locating which terms are present is actually not reflected in this lower bound result. However, this is a lower bound, which is the only one that we are aware of that actually has this m dependence. And the idea of this lower bound is that we do the adaptive experiments can be described by a tree. So each single experiment corresponds to a tree node, and then the measurement outcome of each experiment decide which child node to move to. So everything is described by a tree. And if we're learning Hamiltonian, we're naturally able to distinguish two Hamiltonians that are kind of close together. So for two Hamiltonians that differ slightly, the TV distance will grow gradually, like the TV distance between distributions over these trees will grow gradually as you evolve with the Hamiltonian. So then we also use this Assoy's lemma, which tells us how large the TV distance needs to be in order to successfully distinguish multiple Hamiltonians. So on the one hand, we have an upper bound on the TV distance. On the other hand, we have a lower bound on the TV distance. So using these two things, we'll be able to bound what is the least amount of total evolution time you would need to distinguish a bunch of Hamiltonians in order to, which is a consequence of this learning task. So conclude, we propose an algorithm to learn k-body Hamiltonians with m terms. And with comprehensive sensing, we achieve Heisenberg limited scaling with improved dependence on m compared to previous works. And we have the advantage of using only single qubit control rather than multi-qubit gates. We also present a lower bound result. And there are actually a lot of questions one can ask related to this setting. For example, can we go beyond the k-body assumption? So this was already addressed in the previous work, which I list down here. But in the previous talk, you can if you had been there, then they need they can achieve Heisenberg limit scaling with access to inverse time evolution, or without inverse time evolution, there is no Heisenberg limit scaling. But only very recently we have a several of my colleagues and myself have a new work that can actually go beyond the k-body assumption, still achieve the Heisenberg limit scaling, but without inverse time evolution, just use forward time evolution. And also one can ask, what about Hamiltonian property testing, right? So this is a learning task we're dealing with. So property testing is supposed to be easier, so maybe some of the techniques are transferable. So with that, I want to thank you for your attention.
We have time for questions.
Thanks for the great talk, Yu. So I had a question about the robust phase estimation protocol that you're using. So you're trying to learn the eigenvalues of basically this 2 to the n by 2 to the n unitary matrix. So I thought, in general, you're going to have 2 to the n eigenvalues, right? And so you're going to have to apply robust phase estimation to learn those eigenvalues, which can be done, but requires that you prepare in these like eigenstates of this exponentially large matrix. So I was wondering how, maybe for a few more details about the robust phase estimation.
Right. Yeah. Thanks for the question. So here we actually, so the Hamiltonian is actually extremely easy. Like if we just apply this robust phase estimation, the Hamiltonian here we're dealing with is like a diagonal Hamiltonian, right? So we know what eigenvectors are. So robust phase estimation requires us to have access to the eigenvectors, and we do have this access. Yeah, to clarify, we actually don't estimate eigenvalues because that's unphysical, right? There's a global phase. What we do is we estimate the difference between two eigenvalues. So you prepare a superposition between two eigenvectors, and then you basically just evolve with time, and then the eigenvalue difference will be reflected in your measurement results. And that basically gives you the robust phase estimation procedure that can help you recover the eigenvalue from frequencies.
Okay, gotcha. Thank you very much.
Okay, so again, thanks for the talk. I'm wondering on the previous page 7, when your measurements were noiseless, what are you going to do when there's measurement noise? Could be a binary channel, for example, or if the operators that you're applying are noisy, how do you deal with that stuff?
Yeah, so all the noise is included in this alpha. So you see, we don't exactly need AX equal to Y, but rather we only need AX to be close to Y. You might ask like, Y is not really there, right? You only get a noise estimate of Y. So that is also fine. You can incorporate uncertainty into this alpha. And this optimization is still convex.
Okay, let's thank all our speakers for this session.